Okay, so we're going to be exploring inverses of functions. And that is the focus of lesson 1-4. And to start off looking at inverses, we're going to be talking about a relationship that is really just a set of numbers, and this set of numbers is represented in what's called mapping notation. And you see here that we have a set of values over in this column, and this is called the domain, which is actually referring to like the x coordinate or the inputs, right? So that's the x coordinate in this column, or the inputs. And each of these input values, or x values, are being mapped to a corresponding y value in the range. And so this column over here is the range value. And those are also referred to as the y coordinates. So with mapping notation, basically what's happening is we are showing, instead of an ordered pair form, we're showing how the x coordinate relates to the y coordinate, or the ordered pairs essentially are in the two columns. So the x in this case is -2 and the y is +2. And so we're going to go ahead and take these points and we're going to graph them over here on the coordinate plane. And so I'm going to take a second and graph them, and if you want to pause the video, you can stop and graph them too. So here are these ordered pairs graphed on the coordinate plane. Now the first question that's asked is this a function? So how we know if something is a function is if there is a unique output for any given input value. In other words, for any x value that you choose in the relationship, there should be exactly one y value that goes to it. So I shouldn't have to say, like, if the x value is 1, what's the output? And in this case, the output would be 3, and there is no question about that. There's not a different y value that's mapped to 1, or at any point along this, because if I tell you that the x is 2, then the output is 6. Okay? If I say the input is 5, the output is 6. And if I say the input is 6, the output is 8. And if I say the input is -2, the output is 2. So what that means is that if I give you a specific input or x value, there is a single predictable output that goes along with it. So this is a function. Now another way that I can tell that this relationship is a function is that there is not any place in this domain column here where there's more than one arrow coming out of a value in the x. So in other words, see how there's only one arrow coming out of the -2, only one arrow coming out of the 1, only one out of the 2, only one out of the 5, and only one out of the 6. Now there are 2 arrows going into the 6 in the range column, but that's a different story. We just need to have a unique y value for any given input or x value. And that is the case here. Another way that you can tell if a relationship is a function is by looking at what's called the vertical line test. And you can see if you were to slide a vertical line across this graph, across the coordinate plane, if at any point that vertical line intersected more than one point on a given vertical line, then that would indicate that it was not a function. That's called the vertical line test. Now the inverse of a function actually reverses the domain and range. So inverse sounds like reverse, and that's literally what we're going to do here. We're going to take what were the original y values and make them the x values, so 2, 3, 6, and 8. And we're going to make the original x values now the y values, because with the inverse, we're trying to look at the situation from the other variable's perspective. And so now we're going to look at it as if the x were the y and the y were the x. And so now if I were to show these mappings of these ordered pairs once they were switched around. So originally -2 was mapped with 2, but now 2 will be mapped to -2. Originally 1 was mapped to 3, but now 3 will be mapped to 1. Originally 2 was mapped to 6, but now 6 is going to be mapped to 2. Originally 5 was mapped to 6, but now 6 is going to be mapped to 5. So notice how 6 is being mapped to 2 different values here. So for a given input, if I ask you to tell me if the input or the x value is 6, what's the output? You could say 2 or you could say 5. So right away we can tell that this one is not a function. Let's see, 6 was mapped with 8, so now 8 would be mapped with 6. So that one place where there's two arrows coming out of a domain value, that is exactly why this is not a function, because there are two ordered pairs. For instance, 6, 2, and 6, 5 have the same input but with different outputs. So it's not a predictable output, which means it's not a function. Now if I were to take those ordered pairs and plot those, so plot 2, -2 would be, and if you want to take a minute and pause and graph these, or if you can graph them along with me, so 2, -2, I'm going to go 2 to the right and 2 down, so there's a point. 3 and 1, 6 and 2, 6 and 5, 8 and 6, and what hopefully that you notice is if I also graph the line that the directions said to draw, if I were to draw that line in, which is the line y equals x, and that actually is the line that cuts directly down the first and third quadrants. It's the one where the x and y values are exactly the same. So if the x is 0, the y is 0. If the x is 1, the y is 1. If the x is 2, the y is 2. If the x is -1, the y is -1. And so essentially what happens is this line just splits right through the first and third quadrant. And what I notice in every one of these cases, the point from the original relation is now the reflection in the inverse function. So one way to tell if a relation is an inverse of another is to see if the graphs are reflections of each other over the line y equals x. Now in class we'll talk a little bit more about this classification, but this first relationship that we showed right here, this is actually called a one-to-many function, and it is actually a function. It's just because, see how, I'm sorry, that's not one-to-many. I meant to say that's a many-to-one. Because see how you have two, anything over 1 is called many, and see how there's many or more than one inputs that go to a specific output? So that would be called a many-to-one, whereas in the second one, over here where I circled that little spot where there was two arrows coming out of the sixth, that was a one-to-many. So there's many-to-one in the original, but it's still a function. But in this one, because it's a one-to-many, that's not a function. Now, if instead there was just one arrow going out to one arrow into the range for every single one of these, that would be called one-to-one. But we'll talk more about that in class. Let's take a look at another example. Okay, so what if we wanted to find the inverse of a function like f of x is equal to 2/3 x plus 4. So in other words, one that we have an actual equation to. So when we say the inverse, we're meaning that we really want to see the equation from the other variable's perspective. And so instead of seeing it from f of x, or what we usually refer to as y, we want to see it from x's perspective instead. So first of all, let's look at the graph of this original function. So when we graph a linear function like this, if it's in slope-intercept form, we can just simply plot the y-intercept, which in this case is 4. And then we can use the slope of 2/3 to rise 2 and run 3. So there would be a point there to rise 2 again and run 3. Or we could even go down 2 and left 3. Since they're both negative, that would still make a positive slope. And we could connect them to make the graph of the line of f of x. So now if we wanted to write the equation of the inverse, what we want to do is, again, write it from the other variable's perspective. So the first thing we would want to do is replace the f of x with y so that we actually have a y. And so we'd say y is equal to 2/3 x plus 4. And if we actually just reverse the x and the y, then it would look like this. So see how we just literally took the x and the y and we reversed them in the equation, and that actually is the inverse. But typically in mathematics, we look at an equation from y's perspective, and that's why we're actually really good at graphing specifically this kind of equation, linear equations, when they're solved for y, because then they're in what's called slope-intercept form. And like we just showed, it's really easy then to graph it. So what we want to do secondly would be to solve back for y. So we're going to try to get this equation so that y is all by itself again. And so to do that, we have to follow the correct solving order, which is SADMEP. So SADMEP means the reverse of order of operations, and that means in order to solve an equation, you want to undo in reverse order of operations. So step one would be to undo any adding or subtracting. So we would want to subtract 4 from both sides. And that leaves us with x minus 4 is equal to 2/3 y. And then to get the y by itself, the easiest thing to do would be to, instead of dividing by 2/3, in order to undo that, we could instead multiply by 3/2. And that means we have to multiply the entire other side by 3/2. And when we do that and we distribute that 3/2 through, we end up with 3/2 x, and then 3/2 times minus 4 is minus 6. And that equals y. But then now, to distinguish that from the original equation, we want to go back to using some function notation. And so we actually use this notation, which is actually read the inverse of f of x, or f inverse of x. So we take that and put it back in place of y, and we write our function using this notation as f inverse of x is equal to 3/2 x minus 6. Well, let's go ahead and graph that. I'm going to graph it in red. And when I graph that, I know that the y-intercept is -6. So that's down here at -6. 1, 2, 3, 4, 5, 6. And my slope is now 3/2. So it's up 3 and right 2. Up 3 and right 2. I could go down 3 and I could go left 2 also. But then when I connect, this is my graph. Follow that trend. And as before, when we checked to see if they were inverses of each other, graphically, we drew in that graph of y equals x. And if we do that here, again, just basically the line where the x and the y are the exact same coordinates, and that sort of just runs straight through the first and third quadrants and splits them. And that line, y equals x, now you can clearly see that the two graphs are reflections of each other over it. F inverse of x and f of x. And one way to actually verify that is to look at things like the y-intercept of f of x is the same as the x-intercept of f inverse of x. And you could take any point along f of x and find the coordinates, and you'd find the a point with the reversed coordinates on f inverse of x. So that's graphically how you could tell if these two are actually inverses of each other. In other words, that you didn't make a mistake on doing the inverse, is to look at their graphs, and you could also use a graphing calculator for that. But the more definitive way is using what's called composition of functions. And composition of functions is basically where you take one of the equations and you substitute it in for the input into the other. So like for instance, if I took the original, y equals 2/3 x plus 6, and wherever I saw x, I put in place of it the other function. So again, I'm taking the y equals 2/3 x plus 4, and instead of the x, I'm putting that whole other function in place of it. So I'm going to compose them or combine them together. And when I put that in place of x, if I were to go to simplify this by distributing the 2/3 through, okay, so I'll take 2/3 times 3/2. Well, those cancel out and make 1, so that's just 1x. And if I multiply 2/3 by -6, I get -4. But then there's this plus 4 off the end, and so the -4 and the +4 cancel out and just leave me with x. So it tells me that y is equal to x, and remember that was the line that the two functions, the original and the inverse, were reflections over. Now if we were to do that in the reverse and do the exact same thing but starting with the inverse, y equals 3/2 x minus 6, and in place of the x we actually put in the other function, that 2/3, oops, I'm going to redo that, x plus 4, and if I did that distributing again here with the 3/2 and distributed that through, 3/2 times 2/3 cancels and just leaves me with 1x or just x. 3/2 times 4 is positive 6, and then I had this minus 6 from the function, which then simplifies down to y equals x. And so once again, it simplifies down to y equals x, and so basically one equation undoes the other. It undoes all the operations and gets you right back down to just y equals x, which that's really what we mean when we say inverse. We just mean a function that undoes all the operations to the other and gets you back to y equals x. Thanks for watching. See you in class.